notion of entropy, of course, in standard treatments of thermodynamics, we're used to think that entropy should be related both to the irreversibility and also to the heat that is exchanged with the external environment. So let's imagine that we either take our thermally isolated system and cut it into two pieces, one small piece and a big piece, or we just have the standard situation in which we have a system described by a certain density matrix and a certain environment that is sitting next to it that is very big. And what we have is the entire system is of course thermally isolated. So initially we have a product, a density matrix, and then, so this is where, can you see anything from what I'm writing? You can see it? Okay. So we have this initial density matrix, and then what we do is we time evolve this unitarily on a certain trajectory, and we will go from some initial system environment density matrix to some final system environment density matrix. And we want to define a notion of entropy production for this particular protocol. So we will be inspired in doing this by the Tazaki-Crookes fluctuation theorem that tells you that if you take the ratio of probabilities of a certain forward evolution and a certain backward evolution, right, that is equal to the exponential of entropy production. I mean, that was true for work statistics. In this particular case, I will define the entropy this way. And then I will show you that it has all the properties that look reasonable in thermodynamics. So in order to do so, I have to define trajectories. So it's always about trajectories. It's consuming chalk at the speed of light. So imagine, so in order to define trajectory, before I define a trajectory with a measurement, initial measurement of energy, the initial time and the final time. In this case, I have to keep track of what is the system and what is the environment, right? So therefore, what I'm going to do in order to define the trajectory is initially diagonalize the density matrix in the for the initial state. So both of them. And I will have some probabilities to be in a certain state n. And same thing for the environment. It's not necessarily a thermal state, by the way. And I will use Latin letters for the system, Greek letters for the environment from now on. So once I do this, so I want to define a trajectory. The trajectory is defined by a number of measurements that I do in between my time evolution. Let's stick to two measurements at the beginning and at the end, as when we introduced the Brzezinski quantities. So the first measurement will give me the system in state n mu with probability and this is Q. So once I make this initial measurement, then I time evolve my system. And as I time evolve it, I will have that I started with my product state, but I will end up with a unitary operator. I will end up in something that is certainly not a product state. So write rho prime SE, which is U rho SE. And now the question is, in order to define a trajectory, I need to do a final measurement, right? So what I do is what would an experimentalist do? I first look only at the system. So I trace all the degrees of freedom of the environment and look at rho prime system environment. And this is sum over n p prime m and n. And then I look at the environment only. So I trace over all degrees of freedom of the system rho prime SE. And this is equal to sum over n q prime, sum over mu, q prime mu and well, once I do this, I can define a trajectory by the result of the final measurement that is going to be a state and mu. So it is going to be actually represented by a pair of numbers n and mu that will be obtained with which probability? Well, the probability to measure overall the trajectory n mu is going to be equal to so this I call it gamma as my trajectory, is going to be equal to absolute value of n mu u and mu squared en u. So you see, it has the same structure as the probability that we put in the definition of work statistics last time. So there is a probability to do of initial measurement, right? Measurement of initial state, and then the conditional probability to measure the final state n mu if you measured as initial state n free. Of course, you can think of generalizing everything by putting here, instead of u, something more complicated like the operator t that I defined last time, that defines a quantum trajectory with other measurements. It's something I didn't do yet, but you're more than welcome to do it. You can also publish it, so it's for free. Right, so I don't think it was ever done. In any case, what is interesting now is that this is the probability to measure, so we define this specific trajectory is the probability to measure this forward trajectory. And now we are facing the problem of defining what it means to do a backward evolution.
I was gonna clean it, like wash it so
Is it a problem? Is that a problem, or is the blackboard a problem?
I think that this one, I mean, let's eliminate this first.
Okay, let's eliminate
Yeah.
it.
Sorry.
Yes.
Can you say again what is trajectory is?
What is
Trajectory? Can you give definition again?
mathematical definition?
Physical definition.
So in this particular case, a trajectory is defined essentially as is defined by the result of measurements, right? So you do an initial measurement, you do a final measurement, you have two sets of numbers, quantum numbers, and your trajectory is this result, right? So initial measurement, final measurement. That's
Is
the
it an amplitude
definition.
of,
Sorry?
is it an amplitude of probability to find the final pair of numbers
No,
with the
so
condition?
here I define it as a probability to find this pair of numbers.
But it's equal to them.
No, sorry. Here there's precise.
Sorry.
So there's no equality.
I confused now. Trajectory is probability or just the measurements?
No, the trajectory is. So think about what is a trajectory in classical mechanics. In classical mechanics, the trajectory is this, right? Why? Because you're looking at it. And you see my chalk that moves along in these positions. You can watch it all the time, right? So it's the result of the measurement of your eye, the trajectory. So here I'm generalizing this to a situation in which I cannot watch all the time because I'm a quantum person. So I'm dealing with a quantum object. So a trajectory is something that is the result of, that is represented as by the result of measurements in parameter space. And here I'm doing just two measurements. So this is my simplified trajectory. It's as if I take this and I represent it by the final and initial point, and nothing else, right? So trajectory is, in my language, this,
Okay.
nothing else, okay? Nothing else. So if you do something more complicated, like doing some other measurements in the middle, like as last time when we generalized Jarzynski equality, then trajectory will be something more complicated, like represented by other quantum numbers. But it's the generalization of this concept, essentially. So don't ask me to do it mathematically, because I will not be able to. Let A be. Oh, fantastic. Look at this. Amazing. Thank you. I suspect that we will have to watch it many times.
Yeah.
Anyway, so now that we know what is the probability of a forward trajectory, we have to define what is the backward trajectory, right? What is a backward? There is a seat here. You can turn it off. So, you know, we can proceed essentially the same way, right? We will have rho SE. We will do an initial measurement of that will give us some quantum numbers and a mu. Then we will have an initial state and a mu. We will time evolve it with the dagger, and we will do the final measurement and a mu. And what we will obtain is the probability to do work to go on the backward trajectory that is equal to n mu u dagger n mu squared times the probability to measure in initial measurement the two quantum numbers n and mu. And this probability is what? Is p and mu equal to n mu tilde system environment and mu. Because I didn't tell you what this is. Now the real question is, what do we take as initial density metrics for the backward trajectory? Now, when we proved the Tazaki-Crookes fluctuation theorem, you remember that there was something tricky there, because I compared, so I told you many times that when you write the Jarzynski equality, you start with an initial state that is in equilibrium. You time evolve it, your final state is in some non-equilibrium mess. Still you get e to the beta delta f. But the final state is some non-equilibrium mess. When you do the Tazaki-Crookes fluctuation theorem, I didn't specify it, but I time evolve it forward in time. And the final state is some non-equilibrium mess. I compare this protocol to the backward protocol in which the initial state that is sitting with the final value of the parameter is still in equilibrium with the same initial temperature, with the same inverse temperature I started with. Is it clear? So, all of this to say that if I want to do things in the same spirit, it makes sense to take as rho tilde SE rho prime S, that is what I wrote up here, so is the final density matrix where I traced all the environmental degrees of freedom times rho of freedom, which is the same initial state of the environment that I did initially. Why? Because if this was a thermal state, if rho E was a thermal state that sets the overall temperature, I'm simply telling you I'm starting with the same temperature in the forward evolution and in the backward evolution in this situation. So I'm generalizing that idea. And in this case, what happens is that, right, so this, what happens is that this P and mu is going to be equal to, so P prime n times mu. So if I take this initial state. Wonderful. So now I'm ready using essentially this formula and this formula to define what is the entropy production. I simply, instead of try not to break it. Instead of doing something like Tazaki-Crookes fluctuation in which I prove something, here I'm using that as a definition. So I'm going to say P forward gamma divided by P backward gamma. So those two probabilities is equal to e to the sigma of gamma. So it's equal to the exponential of the entropy production along the trajectory gamma.
Is it gamma or gamma
The
prime?
sigma, sorry. Well, that is gamma.
So not gamma bar. As
Okay, yeah, you're right. Yes, you're right. I should write it like this. Okay? Now, if you take the ratio of these two probabilities, you see that this matrix element and this matrix elements are equal. So you will get just the ratio of these two initial measurements, which is equal to E and Q mu, P prime, and Q. Right, so this is my definition, right? Now, you can well, first of all, you can, using this formula, you can easily convince yourself that e to the minus sigma of gamma averaged over p is equal p forward of gamma is equal to t, right? Because you take this on the other side, you take this here, you sum over all possible trajectories, and, well, the sum on the other side will give you, is normalized to 1. So, that's one thing. Let's see now if this definition makes sense.
Sorry.
Yes.
Is there any physical, if I take a look at your answer, you
Yes.
don't have any information about entertainment and final states. I mean, you don't have Q prime in your answer.
Yes.
Is there any physical reason for this?
Do I have a Q prime in the Tazaki-Crookes fluctuation theorem?
I don't remember.
No, I mean, so in that case, I get P forward W, P minus W, P to the delta W minus, W minus W. Right? So, you see that the tricky thing here is that you never know. I told you many times, you start in equilibrium, your final state is a mess. But so what? you never take care of this mess, right? So the Q prime is the mess, in a sense. You see?
Okay.
So there is no reference to the final state here. You're taking so the trick is that you're taking the ratio between, so the reason you get rid of the final state is because you're taking this ratio, right? So between a forward evolution in which you start with an initial temperature, inverse temperature beta, and a backward evolution in which you start with the same inverse temperature. And then the final state gets erased. So here we are using essentially the same trick, right? So we lose contact with the final state simply because we are taking this ratio. Okay.
Do we assume anything about the environment being big as a bath, or?
At the moment, I don't think I'm assuming. Well, I don't think I'm assuming anything.
Okay.
Am I assuming anything?
Maybe this assumption is included in this,
In this
where we
image- in
said
this
that
we
the
said.
tilde rho is, where the environment part is the same as it was
In a
the
sense, you're
beginning.
right. I mean, yes, I believe that, but in a very philosophical sense that I do not see at the moment. So let me go on and get to the end of the derivation, and then we get back to this point, because it's not clear to me as well. So, which might, but since you're not recording me, I can say. Right?
We are.
Oh, you're recording me? Oh, yeah. So, let's take it. Oh, you're recording. Too bad. Okay. I'll be careful. Not offensive. Okay, so now the question is, the real question that we have is, first of all, if this definition of entropy production makes sense. And in order to see if it makes sense, we want to sort of see if we compare it with our standard ideas from thermodynamics, if we get something easy. And I think that here will come the point that you just raised. So what is sigma? Sigma, the way we define it in thermodynamics, is going to be the average of sigma over all projectors, of little sigma over all projectors. So which means that we have the sum over all gammas defined as this double set of quantum numbers, P of gamma times the log of P and Q mu divided by P prime and Q mu.
Sorry.
Yes.
Sigma is by definition physical reason, and or
Sorry?
what is sigma physically?
This. Sigma is this.
I guess it's just the logarithm
Sigma
of
is
this ratio.
this, is the log of this
Okay.
ratio of probability. At the moment,
Okay, good.
I'm a mathematician.
Okay.
This is sigma. Then now I'm going to show you what it means physically.
Good.
Okay? So I'm going to do physics now. Take this mathematical definition and show you what is physics. So let us explicit. So this P of gamma, we know what it is. I wrote down the formula before. So let's explicitly write it down. It's sum over gamma, sigma of m mu and nu squared Pn q nu, and then we have the log of q, the log of P and q mu minus the log of P prime and q mu. Okay, so then, so what we do now is we play the usual games, right? So we open up this absolute value squared, and then if we do so, we're able to rewrite this with this long formula. So let me first write it, and then I'll explain what it is. And u, then you will have the sum of n mu p and q mu. I suspect that soon I will not have chokes. So someone knows where to get them. And together and okay, we'll make a small break at some point and get the dagger. And then we will have another one that is minus sum over n mu p and q. And then we have n q divided sum over n mu log of p prime and q and q and okay, so I mean This one is essentially this first term written in a fancy way. You see it? You know, I open this up, I put all of this inside, and I put it in between U dagger and you will see why in a second, right? But it's essentially the same as what is written up here for the first part. Yes?
First, somewhere it should be U dagger, and there it should be here, right? Because right now it's U dagger,
No, you're right. So there should be a dagger.
Yes.
So you here, so let me see, you here,
Yes.
and the dagger there, and here you dagger, and here. Now it's complete.
Thank you. And that U and mu is redundant, and
Which one?
in the very end of the line it is just.
There are three.
Ah.
Yeah, it just looks like it's part of the equation, but it's from reverse. Yes, yeah, thank you. That's it.
You're right. Okay. Is it okay? So the first thing is okay with everybody, right? Is this one written up in a fancy way? I just open this up and put the thing inside. Okay?
There should be n, pn in the logarithm.
P N. Yes, it's an N. Yes. And the second one is the same story done with the other term. Open it up, put it inside. Okay? So now the question is, what is the interpretation of this? Can I erase this? Can I? He doesn't anyway. So. Let's see. Okay. Yes.
When we take a sum over m and mu,
Yes.
is it the same as trace u, this object in the middle, u dagger?
Yeah. So that's.
So probably u dagger cancels.
Yeah, they will.
Oh, okay.
Okay. So, well. Yeah, of course. So let me write it. This is equal to trace of. So the way I would write it, which is, you know, you can do what you wanted to erase u and u dagger, or you could be a bit more pedantic, but you will see later on that it's the same. You can write it as trace of rho prime as c, in which you keep the u and u dagger because this is the kind of old log of rho prime as c. Right? So what I did here, I wrote this as so this is the diagonal representation of the initial of rho system environment and log of rho system environment. Agree?
Yep.
And now I put a u dagger, u dagger, and I write it as rho prime c. Trace of rho prime c, not the log of rho prime c. Because I like to write it this way. It would be equivalent to write it as trace of rho log of rho. You will see later on that it's essentially the same. The second one is instead the trace of rho prime SE times the log of rho prime S plus rho. So this is because this is the log of P prime Q mu. So here I reset the initial state, the final state of the environment, to rho E. And here I'm tracing over. No, there is no, it's okay because. So if you write it as a trace, this U dagger is acting on this, and this U is acting on that. So it's
Sorry, but row SC does not commute with U, right?
no.
Okay, so U logarithm row U dagger is not the same like logarithm of U row SC U dagger. So it's like logarithm prime, not a logarithm of row prime. Right?
Oh. No, I think you can do it because, you know, the way I think of it is you expand the log in, well, whatever, you know, and then you put resolutions of the identity everywhere.
Maybe it is simpler just to look at the very first formula, the very first line, and
Yes.
compare it to what you just wrote. And then this is just like absolutely the same formula, more or less.
Oh, okay, yeah. So serious. I'm just.
Assuming that is right, the formula is right. So
Yeah, yeah,
maybe,
okay.
you know, it's a,
Okay.
it can happen that the derivation is wrong. But I
Yeah,
think it's correct
well,
to
it's
set the
okay, yeah.
derivation.
Yeah.
It's like when you write the function of an operator,
Yes.
right? So what is the function of an operator? It's a series expansion. So when I think of the series expansion, I insert.
I'm just a bit confused that this formula can be written for any moment of time for any U, but maybe it's okay. Maybe it's okay.
Ah. Well, so at the end, this term here will cancel out. So that's perhaps the statement that this thing could be written as in any moment of time is perhaps the consequence,
Okay,
or perhaps the reason why this term here will just cancel out of the term.
is my intuition wrong? But this row SE should its
This one?
entropy the whole row. Yes,
Yes.
this one should not. Its entropy should not change, right?
Sorry?
Its entropy should not change.
Yeah, that's exactly the point. So
Yeah,
at
yeah.
the end of the day, this term here will cancel out. But
Yeah.
let me go
Okay.
towards the
But that also
derivation.
answered the question. If we
Now,
apply
the
this
reason I
theory, does
wrote
it
it
change
this
anything?
way, the reason I wrote it in this sophisticated way is simply because this is a relative entropy. So I wanted to, to have the same row prime sitting here to write it as the relative entropy of rho prime ST with respect to rho prime S rho. So this is. So that's the only reason I wrote it in this way. That is perhaps physically not the best way to write it, as you will see in a second. But quantum information people like it because it's a relative entropy. So now the real question we have is, now we want to get rid of all sorts of stupid things. So let us try to indeed get rid of this term because the entropy should not change, the total entropy should not change, etc., and write it in a physical way, not in a quantum information way, which is physical. I mean, it's just mathematically nice, but now we want to understand it in a simpler way. Right, so how do we do it? I think this is already. So No, but it's, come on, I mean, one is left for the chokes, the other left for the,
It will take 5 seconds.
Sorry.
I could send someone to buy another blackboard.
Sorry, can I ask what you try to calculate instead?
Sorry?
What's your goal? What you try to calculate?
I'm trying, so I introduced a notion of entropy, and I'm going to show you that this notion of entropy makes sense, right? So the moment I reduce it, so up to now I told you, this notion of entropy gives you as total entropy production, defining it this way, the relative entropy of the time evolved thing with the one that is split, right? In which the initial state, the state of the environment is reset. So now what I'm going to do is,
They gave me only one.
but this is a big one. Okay. So anyway, right, you should make a revolution and get stone blackboards.
Yeah.
Right? They are more expensive, but the advantage is that you consume much less chalk. So
There is
eventually,
only 2 limiting options, either this, either super fancy, super technological board.
I'm telling you that the stone blackboards are not very expensive. You know, they are made only in Italy, so I'm advertising my country, right? So anyway, so let's go back to this now and do what you want to do, some physics, right? Physical something, right? So this is S trace rho prime log rho prime SE minus trace of rho prime SE log of rho prime cos SE. So now this is equal to, well, so this is the minus the von Neumann entropy, right, of rho prime SE. And this is what? This one is minus the trace over the system of rho prime S log of rho prime S plus minus the trace over the environment of rho prime E log of rho E. If you think about the definition of rho prime S and rho E, rho prime S is the trace over the environment of rho prime E is the trace over the system of. That's what you get. And now we do some cosmetics. So we write this as minus rho S rho prime S E. Now this is minus, this is plus the entropy, the von Neumann entropy of the system, rho prime S. And this is minus trace of rho prime E log of rho. So now I add another one, a big chalk. I have 2 big chalks, right? Thank you. Low density big chalks. I mean, they're much heavier. This one's much heavier. Anyway, so now let me add and divide, add and subtract rho S, S rho S, so the entropy, the von Neumann entropy of initial density matrix. So here I will have S rho S plus S rho E minus S rho prime SE. And here I added the entropy of rho E Therefore I subtracted minus S rho plus minus trace of rho prime E log of rho. Now, why did I do this? Because this is a variation of entropy in the environment, right? In the system. Is the variation of von Neumann entropy in the system over the evolution. So this is delta S system. This one is equal to 0, exactly because of what you said before. The entropy, the total entropy is invariant under time evolution, right? And therefore, an initial entropy, since it's a product state, is the sum of the entropy of the system and the entropy of the environment, because it's a product state, and it's additive. And therefore, this is equal to S rho SE, which is exactly what you said. So there I was just doing it for cosmetic reasons, but it's perfectly fine, and this is equal to 0, right? So what I discover is that sigma is equal to delta S of the system plus that term. Another question is, what is that term? So this term here, if you write it explicitly, you get that is equal to the trace over the environment of rho environment minus rho prime environment times the log of rho environment. Right? So think about what is the definition of von Neumann entropy. So now the point is that if, up to now I never specified what is the initial density matrix of the environment. I just said that I reset it in the backward evolution. But let me assume now that rho environment is proportional to e to the minus beta h of the environment, right? It's some Gibbs distribution. If it is a Gibbs distribution, then you see that this guy here will become beta times the trace of rho prime environment minus rho environment h environment. But rho prime environment is the time evolved forward in time of the environment density matrix. Rho environment is the initial one. So this is nothing but the heat that is exchanged in the time evolution between system and environment. So I'll write it here. Beta E. So what we discover is that this sigma therefore is delta S plus beta E. Ta-da! Makes sense, right? So all this complicated, I'm sorry that I went through all this mess to do something simple, but all this complicated calculation shows you that using this concept of trajectories and this idea of thinking of thermodynamics by comparing forward and backward trajectories, what we did with Dazaki-Crookes fluctuation theorems, you can define in a reasonable way all thermodynamic quantities, and it makes a lot of sense. Yeah, so that's all. Now the point is that this notion of entropy, which is what I would say is the by the way, I have to give you some reference, so you can read everything about this. Where is it? So there is an entire review of modern physics by Nandi Pater Nostro. I don't remember the year, which is devoted to the notion of entropy in quantum information and stochastic quantum thermodynamics. So you can read everything about this there. So all of this derivation, you will find it, well, more or less you will find it in that paper. Right, so what I wanted to say is that, so this is one notion of entropy that makes a lot of sense. You could use it also for thermally isolated systems, even though we have been dealing with open systems in the sense that we split our system into system and environment, and right, we could, we can always take a closed system and split it into two parts. You take just a subsystem that has a small size, a few lattice sites, the rest of the system that is your thermal bath, and you look at what happens when you change parameters and what is the entropy that is produced and the heat that is exchanged by the two parts of your system. But there is another notion, as I was mentioning initially, of entropy production that was introduced by Anatoly Pulkovnikov in order to characterize, in a sense, how reversible or irreversible is the quantum evolution of a thermally isolated system. So you just take a system that is closed and you think of how let's try the big chores. So you think of how the system, you want to characterize how reversible is the dynamics. And the way you do it is by thinking about the system in terms of the adiabatic theorem in quantum mechanics. So you have a system that depends on a certain parameter, lambda t, that you're varying in time, and at each instant of time you can think of diagonalizing this Hamiltonian and construct what is known as the adiabatic basis. So you will have your psi of lambda t, psi n of lambda t, and your En of lambda t, which are your eigenvalues and eigenstates. And now you time evolve your system. You start with some initial condition, and you time evolve it. And when you time evolve it, you can always think at each instant of time to represent the time evolution in the adiabatic basis, right? So you will always get sum over n equal minus I En lambda t t Cn lambda t, and then psi n lambda t. Right, so adiabaticity would mean, the fact that the evolution is adiabatic, and here we could enter an enormous discussion of how you keep a quantum evolution adiabatic, counter-adiabatic terms in Hamiltonian, etc., but it's very complicated. So let me skip it completely, but for those of you who are interested, again, I think Tolia wrote also a review on adiabatic something, so you can find it online. But the interesting thing is, so the evolution is adiabatic whenever, essentially, if you start with a given set of these coefficients, you don't have transitions among different energy levels, right? So if you start, for example, in the ground state in which C naught is equal to 1 and all the others are equal to 0, then C naught will stay equal to 1 always and all the others will stay equal to 0 always. But this is not the only possibility. You could also have a certain coherent sum here. And what is important is that your state follows adiabatically your system without transitions, which means essentially that your coefficients are not changing. So, in absolute value. So, the way to characterize this is by stating that, so what you can do is you can define the probability to be in the nth state as a function of time, call it Cn lambda t, and a way to state what I just said in words is to say that if I construct given this probability distribution, if I construct the Shannon entropy of the probability distribution, which is minus sum over n Pn log of Pn, then whenever I'm adiabatic, this entropy is invariant, right? It doesn't change. Whenever I'm not adiabatic, the entropy is changing. So in particular, now the problem is that, right, so this is, for a many-body system, it's a good notion of entropy that is able to encode the idea of reversibility. So if the diagonal entropy grows, then you never be able to get back to the same initial state by reverting the time evolution. However, it's not really, it's not that straightforward, right? If you think about the Landau-Zener problem, for example, right? So that we discussed last time. Imagine that you start somewhere here, so time is running this way. Right, so you start here, you time evolve your system, at the end you will end up in some superposition of this state and this one, right? And now, so I imagine that I'm, if the parameter that I'm varying is the diagonal energy. So I imagine that my time evolution goes like this. Goes up, and then, the question is, as I already said, if I turn it back, so I revert this time evolution back to the same initial state I started with. So this is epsilon of t, and this is t. Will I get back to the same initial state I started with? In general, no. But it could also be yes. So, do you think you would be able to hook up a simple protocol to come back to the same initial state in this situation? To tell an experimentalist how to get back exactly to the same initial state.
Yeah, it is. I know it's possible because there are works on non-adiabatic state preparation.
Yeah, yes, but that would be very complicated to do that. So it is possible, yes. It is simple.
If we will start from the eigenstate of the initial Hamiltonian,
Yes.
and during the whole evolution, distance between this level and others will be not less than like a constant, so we don't have such Landau-Zener transition, and we will.
Oh, okay. If
in
you're
general, we will
adiabatic,
stay
if
in
you're
the same.
adiabatic,
Of
okay.
course.
If you're adiabatic, yes. But imagine that you're not adiabatic, so you generate a diagonal entropy. You're not super. If you're super slow, I agree. So then, in that case, this definition of entropy would make a lot of sense, right? You're saying I'm not producing any entropy, and therefore that means that if I revert my time evolution, I will get back to the same initial state. So this notion of entropy is also connected to the notion of irreversibility. But what I'm trying to criticize is it really connected to the notion of irreversibility in this simple sense? So, in particular, imagine that you do this protocol and you time revert it back. And you will not get back to the same initial state, I can tell you. If you don't believe me, take the parabolic cylinder functions of Mr. Zenner and do the calculation.
Yeah, that's clear in case of such Landau-Zenner, because in this case, distance between relevance comes to about a zero. So
Yes.
you will have a probability to go to another adiabatic eigenvalue.
But
So
the
yeah.
question is, can you cook up a protocol that is very similar to this one, actually not very different, in which you come back exactly to the same initial state? So let me tell you, if you go from here to here and you stay here for some well-chosen time, and then you revert your evolution, you will come back to the same initial state. You just have to wait. Why?
Well, the transition probability depends on the speed with which you're going through this point.
Mm-hmm.
So if you're slow down at this point, the probability will go to.
No, I don't think it's a matter. So it's actually the fact that here we are dealing with a, unlike the standard notion of entropy and standard thermodynamics, here we are dealing with a notion of irreversibility that is not strictly connected to dissipation, but is connected to the fact that time evolution in a many-body system is complex. So in this particular case is not. So let me tell you how you can, let me show you in a simple way how you can revert it. So what is the analog of a Landau-Zenner transition? The analog of a Landau-Zenner transition is I'm starting in some quantum state. I pass through quantum mechanically through this point in time, which means that I'm splitting the probabilities. I have a certain probability to stay down, certain probability to go up. Then, I stay in these two guys, and then here, if I revert to the time evolution, it means that I'm passing through this point again, which means that I'm again splitting the amplitudes to go one way or to go another. So, have you ever seen such object? It's a Mach-Zehnder interferometer. So that if you do a reverse evolution, it's like a Mach-Zehnder interferometer in time, in a sense. You're starting with your beam here, you time evolve it, you go through the first beam splitter, that is the first avoided crossing. Then you time evolve in the two states. Then you go back, you conjure this, again to pass against in the beam splitter, and then you come back to the same state. Now, in this particular case, you know perfectly well that you could decide to end up here or there, depending on what is the optical path that you're choosing in between. And what I'm trying to convince you of is that, and then you can prove it using parabolic cylinder functions, etc., or numerically, is that if you do this time evolution, and here you wait for some time, which means you let the states acquire appropriate phases, then eventually you will be able to revert your evolution and come back exactly to the same initial state. So, the notion of all of this I'm telling you because whenever you produce diagonal entropy, it doesn't strictly speaking mean that you're not able to revert your evolution and to come back to the same initial state. Because since you don't have dissipation, your density matrix has all the coherences in place and you still keep that information. If you're able to use it as we are using it there, you will come back to the same initial state. So that entropy is not a notion of irreversibility in a thermodynamic sense, but it's a notion of irreversibility in the sense that if you have a many-body system and you time evolve it and you pass through many such avoided crossings, which is by the way the case if you have a non-integrable system, then if you try to revert back time evolution, in practice it's impossible. It's impossible because you're never going to be able to find the conditions to satisfy all the constraints that will allow you to get back to the same initial state, right? So, but you're not dissipating any energy. It's not irreversible in the usual sense. It's not irreversible as when I turn on light in this room. So when I turn on light in this room and I switch it off, well, the state of the universe at the end is not the same as the state of the universe at the beginning, and I will never be able to get back because I emitted light, the bulbs emitted light and dissipated energy. So in this case, you don't dissipate energy, anything. Okay? Is it clear? No. Perhaps. Think about it. Okay?
So, do I understand correctly that this is in principle just the same as we have, I don't know, if we think about single particle problem, we'll have a random oscillations, right?
Yes.
In two-level system.
Yes.
And if I will wait for some specific time, then I will get back to the initial state.
Yes.
And then, as far as we have many-body problems, we have a lot of very complicated system, and this I don't know, way to think about that would be just one sign, but it would be something more complicated. But in principle, we're still talking about the same situation where if we will somehow manage to find this point in time, we'll get back to the initial state.
In a sense, yes. Look, let me try to synthesize what I said because I think we need a synthesis. What I'm trying to say here is that this entropy measures the lack of adiabaticity. Not to be adiabatic in quantum mechanics doesn't mean in principle that you're not reversible. Okay? That the dynamics is not reversible. You can find situations, simple situations like this one, in which it is reversible if you tune your weight or you choose your parameters properly. But it's complicated in general. So in practice it is irreversible, but not in principle. Okay? All right. So now that we did this, we understand everything about entropy, well, more or less. The question is, can we Okay, so the question is, can we use this to do something more sophisticated? So what we are going to do now is I'm going to show you a case, a particular case in which this lack of adiabaticity gives you some interesting physics. If you combine the lack of adiabaticity and the presence of practical irreversibility with with many-body physics. And the story takes the name of two guys, Hubble and Dirac. So, who many years ago asked themselves the question, imagine that I have a classical system, right? I have this is temperature, and I have some second order phase transition, TC, and I take my system, think about the ferromagnet to paramagnet to ferromagnet transition. So I start in the paramagnetic phase, here is the ferromagnetic phase, and I then slowly cool down the system through the critical temperature, right? So, and then after I do this, do it reasonably quick, but not too quick, I look at the state, thermodynamic state that I reach at the end. Now, the observation they had is that if you do so, because of a phenomenon that I hope you know about, that is called the critical slowing down. So the fact that the relaxation, not only the correlation length goes to infinity at the second order transition, but also the relaxation length blows up at the second order transition. So in practice, your system is not able to relax, to readjust to the state. Then because of this, you will go through the second order transition, and then eventually here you would not be able to be at the end of the evolution in the same thermodynamic state that was expected if you had this final temperature. Because you would have the presence of some domain walls, some defects that are the leftovers of the fact that you cannot relax by passing at a finite speed through the phase transition. Now, it's a sort of lack of adiabaticity because of critical slowing down. Okay? If you would be able to evolve adiabatically, so you'd be able to pass through a second order transition and change adiabatically the state and see your magnetization growing, etc., etc. Well, this is impossible. This is the state. But the thing is, it's impossible in a nice way. This was the observation of these two guys. Because if you think about, so let us do what is standard in the theory of phase transitions. So we introduce something called the reduced temperature, T minus Tc divided by Tc, and we imagine changing this reduced temperature in time at a certain speed with a certain time scale tau q through a second order transition. And the second order transition, as I told you, is characterized by the correlation length blowing up to infinity with a critical exponent mu, and the relaxation rate, the relaxation time going to infinity as well, with an exponent that is minus mu times z, where z is called the dynamical critical exponent, and it essentially tells you what is the asymmetry between time and space in your system. Right? Have you ever seen this? Good. Right, so now let's apply this knowledge to this particular problem. We are cooling down our system at a finite speed, and we want to estimate the number of defects that will be left over by passing through this region in which you're not able to relax. So the way, so let me write first the final result, and then I'll tell you what is the argument with which you get it. the final result is that the density of defects is going to be proportional to tau q, this time scale, to the power minus mu d divided by 1 plus mu z. Where mu is the correlation length exponent, z is the dynamical critical exponent, and d is the dimensionality of your system. Now, as I told you, it's breaking at the abaticity, the statement of Kibble and Zurek is that this system is breaking at the abaticity in a nice way, because the number of defects that you get out of this time evolution is actually determined on scales in a nice way with universal exponent in terms of the speed with which you're varying your parameters. So, before I prove it, let me tell you something. In classical system, you'll never see this. I mean, you have to be really lucky. And the reason is that classical systems are not thermally isolated in practice. So the dynamics of a classical system is the critical dynamics of a classical system is due to dissipation, is due to the coupling of some environment. So energy is exchanged with this environment. And in practice, when you do the time evolution, even if you do it relatively fast, when you do the time evolution through the critical point and you pass through the critical point, you have, in addition to the creation of these defects because of critical slowing down, you have another phenomenon that is called coarsening dynamics that essentially makes it impossible to see the scaling because you nucleate the defects, but they start moving immediately in a loose sense. The interfaces start propagating through the system. So, nevertheless, let me just derive this result as if coarsening was absent. So, as if this system just creates defects and then they stay there. And the argument by Igor and Zurek is the following. So in this, if I change linearly my temperature, I will have a region in which I'm essentially adiabatic. So I'm varying my parameters low enough, but the speed at which I'm varying is such that the typical time scale of relaxation is still relatively small, so I'm following the thermodynamic state. But then at some point it blows up, and I enter what is known as the sudden region. Sudden region means I'm not able to relax anymore, because I'm changing my parameters too fast as compared to the typical relaxation times. So how do I estimate when I'm sitting in the sudden region? I compare the typical time scale of variation of my parameters to the time scale of relaxation compared to tau, which is epsilon to the power minus mu z. And therefore, I obtain that as a function of time, I will enter the sudden region, or I will be in the sudden regions 4 times the tau q mu z divided by 1 plus mu z. Now, inside the sudden region, I'm assuming that the state of my system doesn't change. So if I had a certain correlation length here, I will have the same correlation length here. And since the correlation length is roughly the only length scale that I have in my problem, that will give me also the typical size of my domain walls once I leave the sudden region. So what I did then was to take this, estimate by putting it, by looking at how epsilon depends on time, which was minus t divided by tau q. then I can estimate what is the correlation length when I leave the southern region, and that is going to be equal to tau q to the power mu divided by 1 plus mu z. And then, given this, I can immediately obtain the number of defects as psi to the power minus 3. Sorry, the density of defects I can estimate is as psi to the power minus 3. And that is the result of the calculation. Very simple. So you get the nature of this. Right. So now it's obvious that we can ask now the question, well, if here instead of temperature I take a quantum system that has a certain parameter lambda and has a phase transition with a certain lambda c, and I'm varying this parameter with this mode, and well, I assume that you're using the lambda c. And yes?
Just last question. So this end effect, I can more or less think of it like the number of domains.
Yeah,
inside
number
the
of
system.
domains, yes. Number of domains that are left.
Yeah. Okay. Yes.
Right. Right. So, okay, so what I wanted to say is that imagine now that instead of you start translating all this story from the classical phase transition to a quantum phase transition. Instead of having temperature, you have a parameter. This parameter this Hamiltonian has a quantum phase transition at a certain critical value of lambda equal to lambda c. At this critical value of phase transition, what you have is that your gap in the system, the quantum mechanical gap in the system, goes to 0 as lambda minus lambda c to the power mu times z. Right? But the gap is essentially a time scale if you take the inverse, right? So it tells you also that the system is not able to readjust. The fact that the gap is going to 0, it means that you will not be able to go through a quantum phase transition adiabatically. So you will have also in the quantum case an adiabatic region, and then as you get through the phase transition because of this vanishing of the gap, you will have a sudden region in which you're not able to readjust the state of the system to the time evolution. And then you get out of this sudden region, you will have a certain correlation length, and then you will estimate the number of defects. Is something going to change? Nothing, right? I mean, the whole thing will go through from the beginning to the end. And this is indeed what was proven by a number of people between 2005 and 2008, Zoller, Zurek, Polkovnikov, etc., etc., etc. So now, we have to finish now, but what I want to do next, after the break, is show you very quickly a nice calculation that I think is one of the few calculations that were done on this subject. I mean, this I would not consider it a calculation. This is number I mean, it's an argument, right? But the nice calculation is something that was is something that was that was done by Churg and Levitov around the same time, 2008. I don't remember the time. So they essentially took this problem for the quantum Ising chain, And they solve it from the beginning to the end. They computed the probability to generate defects. They also did the calculation for correlation functions, but that is too complicated. So I will show you how this calculation goes, because it's a nice combination of the Landau-Zenner problem and many-body physics. And then, perhaps by looking at that calculation, you will see also why in the many-body context that to revert the dynamics is practically impossible, right? Because it's practically too difficult to combine all the conditions and get back to the same initial state. Okay, questions? Okay, no questions, next speaker.